On behalf of a number of people that I'm working with here at the PODAC, including a contractor at APR, Dean Henze. So it's Victoria McDonald, Nikki Tabaldi, Jorge Vasquez. We all work at JPL, and Dean Henze works in the PODAC through this company called APR Corporation. Next slide, please. And I'll just do a quick, I control the slides, sorry. Just a quick mea culpa. I don't think I'll get through my whole talk here. I had I have too many slides, but I'm going to reprise some of the thoughts on the cloud format optimization for the session on the GDS2 evolution if I don't get around to it. Okay, this is just our general slide of, this new era of users working with the GRIS data and really any of the NASA Earth Science data products, either directly in the cloud or streaming data from the cloud to a local computer. This is we're doing the scientific analysis in the cloud. I mean, that's the point of this talk, as you'll see, but you can still download. This talk is not about actually downloading and working locally, but of course you can still do that for sure. And if you stop by my poster later, there's a number of tools and services we can offer to the user. A nice command line utility called PODAC Data Downloader. I actually ran a training session on that at the last conference in India that went quite well. And probably if you have Python already installed in your laptop, we probably can get you up and going with that nice program in 10 minutes or so. All right, so today I'm going to extend some of the stuff that I presented on last time and talk about really some of the new things we've been working with doing computing actually in the cloud using a variety of Amazon Web Services. The first one I'm going to talk about and really focus it on is this parallelized application or a computing application we're doing using Dask and this new third-party system called Coiled. So Dask, of course, is the Python package you use for parallelizing and doing parallel operations of your scientific code. And Coiled is like a wrapper around it. So it's you can think of it as a Dask management system, and it's really quite elegant. Some of the things we're going to be reporting on are the metrics are performance, speed, and reproducibility. So I'll talk about two cloud computing applications. I'm actually the second one I'm going to update you on what I introduced last time with regards to doing time series analysis using AWS Lambda. We've made some progress on that as well. And if I have time, then I'm going to talk about the HDF NetCDF container optimization. Some of the things that I've learned recently over the last year. Actually, I work on the NISAR mission too. As part of my time as JPL, and they have a product in HDF5 that they've optimized for the cloud. And if I have even more time, I'll talk about some of the stuff we're doing with Kerchunk and Czar. But again, the last two bullets, probably I'll dive in that this afternoon in the GDS2 evolution session. Okay, so the core computing component of in the cloud, of course, is the EC2. That's the Elastic Cloud Compute. It's a virtual machine that you rent, right? And you install your software, run your code, and do your stuff. It comes with a variety of different flavors, of course, of processors and memories that all increase in cost. And Dask then is the Python package that provides the options for doing the parallelization of your code and the computations. And you use that in conjunction with the EC2 instance of these various size to accelerate the computations and reduce the time of your computations. So Coiled, what is Coiled? This is actually an independent third-party software system for managing a Dask cluster. And so again, it's like a wrapper around the Dask system. It kind of hides the complexity of setting up and running Dask. The guys that are in this company and who founded this company are actually some of the inventors of Dask, of the ones who the coding community that came up with Dask. And so it's the commercial arm of Dask. It's a software as a service. You have to pay, but there is, as I'll describe, there's a free trial available. All right. Sorry, I have to look at my screen here. Okay, this table here really depicts some of the challenges for using the cloud as a software and a service, and really the knowledge and expertise you need to function in the cloud successfully, right? And so there's a lot of things that you need to be aware of besides being a Python coder and knowing using things like Xarray and applying Dask and parallelizing. So you have to understand what parts of the code can be parallelized and how to parallelize it. You have to think about how to optimize the code and the cluster. And within the AWS infrastructure, there's another layer of complexity there as well. You have to understand about how to spin up an EC2. You might have to know something about the Lambda functions and other types of requirements, and of course, keep track of cost. And additional software technical knowledge, you might have to know about Dockers, of course, Linux shell bashing, and very importantly, these VMs often need credentials and various software environments. So there's a high level of complexity. And the nice thing about Coiled, it hides so much of this complexity, especially in the last two columns with regards to getting things going in AWS, spinning up your EC2s, managing your Dask cluster. Those types of things, it very elegantly hides from the user, and that's the strong benefit of using this coiled system. So you really just have to try it to see the benefits. Maybe I'm kind of like shortchanging it here. I'm not really describing it to the level that that you would really appreciate its benefits. So how do you get going in the coil environment? Well, it's really simple. You just you could sign up via GitHub to get a coiled account, and then you just download pip install coiled and connect it to your AWS account. So you have to have an existing account, AWS account, to say spin up EC2s. Those costs are on your own. But the nice thing about coils to get going for the user is that the first 10,000 compute hours per month are free. Now, is that a rolling offer? So the next month is free? I'm not really sure about that, but the computing costs beyond the first 10,000 CPU hours are quite reasonable at 5 cents a CPU hour. And so again, the Dask system is one that hides the complexity and actually will just spin up the number of CPUs that you need to successfully run your problem. So in some ways, it's both practical for reducing the management complexity of the Dask cluster and potentially reducing the cost of your operation. So how have we applied coiled here? So we ran a little test here, a little experiment to do sea surface temperature and SSH correlation. And so we had two products, gridded measures SSH, and we're also using the AVHR OI global product at, actually, I think that's a remote sensing system microwave OI product at 1/4 degree. They do line up in the period of 1998 to 2022. And so what we did is we're extracting out the daily maps. We refactor the SST to downscale it to the SSH grid. And then we're just running a kind of like a sliding correlation problem where in the 6 degree by 6 degree box, we're locating and co-locating the data. We're fitting 2D linear surfaces to the SSH and the SST, and then calculating the anomalies, which are the deviations from those 2D fits, and then running the correlation between those two outputs, right? And so it actually ends up to be 2 million windows per pair of files. And so the number of files is actually 1,800, so 3,600 in total. The volume is not that big, it's 20 gigabytes. And so this is just the simplistic calculation that we're doing. But it actually takes a fair amount of time to run this calculation. So if you were to run this calculation, it takes about 25 minutes to processing time for each pair that you look at. So about a 1 month if you were to run this locally on your laptop or an EC2 instance if you didn't have do any parallelization. So that's a significant amount of time just to run this, this kind of very straightforward correlation analysis. But you parallelize it and you run it with coil, and it sets up 250 50 workers. It can take this same calculation down to 5 hours, and it's going to cost you $20 in AWS cost, no coil cost. We're just getting within our free tier. So that's a significant savings, a radically significant savings in time for just $20. I think that's a pretty good trade-off. All right. So in summary, COIL really allows the scientist to, to focus in on the scientific code and the results and really abstract the implementation of the parallelization problem. The free compute tier is going to meet most use cases, but again, maybe, as a caveat, this is not really a total silver bullet, right? You still need some expertise, of course, in Python and the compute strategies to identify, which parts of the code would be good for parallelization applications. But the whole management of say the DAS cluster, that's what really the COIL provides, and its advantage of using it, and it's both cost savings and a time savings. For the scientist who wants to do say like run a parallel compute exercise in the cloud. All right. I did report last time about some of the stuff we've been doing with Lambda. So Lambda is a little bit different service. It's best for discrete tasks where processes don't need to communicate with each other. So you're only limited to 15 minutes of compute time with these Lambda services, and you only have 10 gigabytes of temporary storage. But the cool thing is you can like spin up a lot of these at very low cost. So there can be 1,000 concurrent executions that you can set up using these lambdas. And so we ran this little experiment that I believe I reported last time, where we just took a few grist products, in this case the Mir 25 and the Mir 1 kilometer, and just the problem was just completely compute a global average over a 1-year time cycle. Right, so just take all the data. Each lambda would attack one file, right, out of the year. So we had 365 lambda instances, and then calculate the mean. And how much does that cost? Well, the cost is actually it's very it's under $1. It's 72 cents, and this particular problem ran on the order of, I believe, minutes to get the output. And if you want to scale this up for like 10 years, it's also a reasonable $7. So another straightforward strategy of using the cloud to do simple scientific calculations. We did really want to extend this concept to be able to do pixel by pixel comparisons, with the idea that eventually we could build a system to do things that like the Gimpy does, but at much higher resolution. And we haven't we've made some progress on that, but we ran into some bottlenecks. I'm not going to report what those bottlenecks are, but we're actually looking at different strategies. But we wanted to use Lambda to actually just extract out, explode each file to a point per time and store that into another format that's optimized for cloud, that's Parquet, and then do the statistics on those Parquet files through time. But unfortunately, we ran into I would say like a exploding cost when we scaled this up, because each one of those operations of like exploding the files and aggregate organizing them into individual files and then doing the statistics, you pay for each one of those operations, and there was like a kind of an exponential rise in cost there. So this wasn't the roadmap to go for that particular problem. We're looking at other strategies, including using COIL to do this. But I just thought I'd report to you that this is where we kind of left off with this particular problem. How am I doing for time, by the way? Okay, I think I'm just gonna like introduce. That's what I wanted to say about cloud computing and the cloud and our experiences. My next topic, I wanted to introduce this cloud optimization that, again, I've been working with via the NISAR project, and I think it has some ramifications for us in GRIST as well. And that is that HDF and NetCDF is an HDF file. They don't work well in their current format in the cloud, and that's because their internal metadata has not been optimized for cloud reads. Of course, compared to local disk read, there's a longer latency for reading objects in S3 buckets in the cloud, and so you want to minimize that latency as much as possible. And I'll describe this afternoon. There's some strategies for reorganizing the internal contents of the HDF file so that's internal metadata. And this is not the global header metadata, but this is the metadata actually tells an H5 or a NetCDF reader where to go in the file to read something. That metadata can be aggregated and optimized. And so that's what I'll describe in the afternoon here. And I think I'll just leave the point that this is a work in progress with regards to NetCDF, because NetCDF has a different library, of course, and some of these paged aggregation features cannot be directly implemented using the native NetCDF libraries. But there may be ways of around that where we can implement this strategy for future data sets. So yeah, I'll talk about this more again in the morning, and I think I'll just go to, or later this afternoon, and I think I'll just go to my conclusion slide here. This is just a very generic conclusion slide that I presented. This some examples of working in this ecosystem, new ecosystem of scientific computing. Requires new knowledge and skills and techniques, but coiled is perhaps one of the ways forward to streamline parallel computing applications in the cloud. And I did mention we have some tutorials on our GitHub site that actually do these tutorials that I described right here. So you actually can take some of this stuff, and once you get set up with your COIL account, you can just take them and run them. And I'll talk about the HDF5 and the NetCDF internal metadata optimization later today. And yeah, what I'd like to leave you, the message here is that we're really here to help you on this cloud journey. And so we have this nice cookbook that Garrett mentioned that actually has levers. So there's a lot of good examples and tutorials you can take right there. There's actually a chapter in there on GRIST. And yeah, if you actually have tutorials that you've developed that you think would be of interest to the community, we'd like to get up in the cookbook as well. So I think I'll end right there. Thank you. Have a time for a question? Maybe we'll take one question. David?
So are there discussions between NASA, EUMETSAT, NOAA, and the various agencies producing satellite products about how to unify the access approaches across the entire cloud universe? EUMETSAT's got its own set of cloud things. NOAA is working on a different cloud from what NASA is working on, and all of these data transfers between clouds start to become an issue as well, on top of the programming things. So are there talks at high levels about how to smooth all of that?
I'm not personally involved with those talks, but there are talks, I guess, ongoing. I don't really have a good answer. I would kind of defer, perhaps maybe we can go into the discussion section. Maybe Ken Casey could attack that problem because he's working exactly on this issue. Of course, we're in NASA. I think I did mention that we're in the AWS West system. So if you stay within that region, it's, you have higher performance and no egress cost. Once you move data from region to region or cloud provider to cloud provider, there are some potential egress costs depending on what agreements have been negotiated with the different cloud providers. But for the NASA, there's no cost to egress out of AWS really anywhere to your local computer if you want to take it to another cloud. So there's that to consider. Thank you, but that's a good point. Thank you, David.